Hi there, today's lesson is Unit 1, Lesson 10, Composing Figures. What we're going to do today is hopefully we're going to take all of the things that we've been learning in the previous 9 lessons and putting it all together to start synthesizing and the use of these rules that we've been learning about composing figures. We've talked about corresponding angles and corresponding points and corresponding segments. And what we've talked about with those pieces is that all of those parts remain the same measurements as we do any kind of rigid transformation. So today as we work, we're going to be working without using any kind of measurement tools except for the drawings that we have and the measurements that are already given to us. So as we're going to look right here, we're going to use reasoning about rigid transformation to find measurements without measuring. Today is the day that we get to use all of those thoughts we've had and tie everything together to say this is what basic rigid motion is, rigid transformation is, and this is how I can use it. The first thing here is here's a triangle. Mine looks a little different. I thought I was recording before and realized I hadn't hit start, so I just left it there. So here's what we're after with this. We're supposed to take triangle ABC over line AB. So right here, I took this triangle right here and then reflected it across right here and drew it there. And then I'm supposed to label the image of C as C prime. From there, I'm going to take this triangle and rotate triangle ABC prime around A so that C prime matches up with B. And what we see with that is that under that rotation, we bring it just right back to here, and we see that these two triangles are exactly the same. So what can you say about the measures of angle B and C? Well, the measures of angle B and C, when you consider these pieces right here, this angle right here is the image of angle B. Therefore, it's the exact same as this angle B. What that means with this is when I go ahead and rotate, this angle B right here is also the exact same measure of angle C. So we can say measure of angle B is equal to the measure of angle C. And we can say that because of basic rigid motion. We recognize that under rigid transformation, the angle measures are preserved under that rotation. Here's another triangle. We were supposed to draw the midpoint M on side AC. The way that I found that midpoint, you'll have to forgive me, I have a broken ruler here, is I found the distance from A to C, which is 6 centimeters. I know that because 10 to 6 is 6 centimeters, and so I put a point right in the middle, 3 centimeters there. My job now is to rotate this triangle 180 degrees using M as the center to form another triangle, to form triangle CDA. So that means I'm going to use, D has not been a part of this yet, but I'm going to go ahead and have a third point. It's going to come across here, and it's going to be point D. Okay, so 180 degrees around point M. Recall a couple lessons ago in lesson 8, we talked about a rotation of 180 degrees around a midpoint and maps this segment directly back to itself. The only thing that's going to change is A is going to move to here and C is going to move to here. And we see that we come up with two triangles that are next to each other. Go ahead and mark my new point right here. This is point D. Connect the lines to create our figure. Draw our new triangle. We still have midpoint M there, which did not move. And now we have some questions to answer. What kind of quadrilateral is A, B, C, D? Using the properties of rigid motion, we have a few things to consider and a few things to remember, specifically about this, a 180 degree rotation. Recall that under a 180 degree rotation, we have one of the consequences of that is lines that are rotated, their image will be parallel to each other. So their corresponding segments must be parallel to each other. What that tells us is that this segment right here, segment BC, is corresponding with segment AD. And since those two are corresponding, and since segment AB corresponds with segment CD, I know for a fact under that 180-degree rotation that segment AD and segment BC are parallel. Segment AB and segment DC are parallel. And since this has two sides, right, two sets of sides that are parallel, I can say that this quadrilateral ABCD is a parallelogram. And I can say that because under the rules of 180-degree rotation, 180-degree rotation the image of 180-degree rotation of lines or segments is parallel to the original. So under that 180-degree rotation, corresponding sides AD and BC, and then AB and CD are definitely going to be parallel because of that 180-degree rotation. Oops. Next one, this activity, we made a parallelogram by taking a triangle and its image under 180-degree rotation around a midpoint of a side. This picture helps you justify a well-known formula for the area of a triangle. What is that formula and how does the figure help justify it? Well, that's kind of a big question with this. A well-known formula for the area of a triangle is that the area is equal to 1/2 of the area of a rectangle. We know that the area of a rectangle is length times width. When we work on the area of a rectangle, we know that a rectangle is something like this. Under this figure, when we find the area of a parallelogram, we do the same thing as we do with any rectangle. We take the measurement of the width or the height, and we multiply it by the length or the base. And in this case, what we see is when we take 1/2 of that, if I were to find the area of this parallelogram and just go length times width or base times height, I can cut that in two and I find the measurement of the area of the two figures. Therefore, our area of formula for the area of a triangle is justified because that triangle is 1/2 the area of the quadrilateral. So, interesting fact for you. So let's look at the next one. This picture shows three triangles. Triangle 2 and Triangle 3 are the images of Triangle 1. So we know that each of these triangles, under this rationale, 2 and 3 are images of Triangle 1. We know that each of these three triangles are exactly the same triangle. Just these two, they appear to be rotated 180 degrees around one of the points and probably translated to another point. Describe a rigid transformation that takes Triangle 1 to Triangle 2. And what points in Triangle 2 correspond to A, B, C, or A, B, and C in the original triangle? When we take a look at this triangle then, we'll go ahead and put Triangle 1 into our tracing paper so we can see what happens here. Here's Triangle 1, here's B, here's A, and C. Now our first thought might be, well, maybe if I just reflect this across the line, that will work. And we could see, a reflection across line AC does not match that up. So we're not going to use that kind of reflection. What we can do, what I would suggest that you do whenever you're approaching this to decide, describe a rigid transformation that takes triangle to triangle, or any figure to another figure, is always match up the corresponding points first before you do a rotation, or match up a set of corresponding sides before you do a reflection. Take that into account. And here, let's go ahead and answer this. what points in triangle 2 correspond to points A, B, and C in the original triangle? Well, I know that the top of the triangle is the same as C. So as I look at this and I bring that down to there, I can see a little bit of a different relationship than I saw by just looking at it from up here. By connecting C and A, recognizing that A corresponds with C, I can see a different kind of relationship. What I notice is that it appears that BC and AD are parallel, and what we've been practicing is that a 180-degree rotation around a center point makes parallel lines. So if I rotate this 180 degrees around center A, I see a mapped image. So there's my description here. Let's go ahead and describe that. We say for triangle 1, we're going to do translate triangle 1 from A to C, and then rotate 180 degrees around center C, so that the whole triangle matches each other. And then I need to finish my last little spot. A corresponds with C, B with D, and C with A. Okay, there's those pieces. Well, what kind of a rigid transformation takes triangle 1 to triangle 3? What points in triangle 3 correspond to points A, B, and C in the original triangle? Well, let's take again into account the same thing. Let's go ahead and translate, find corresponding points, A, B, and C, one corresponding point that goes to here. I think using our last example is a good one. We can put that right there, and we see that there's a 180-degree angle, or a rotational angle. Or what if you say, you know what, I actually want to translate B to A instead, and go up here. And we can see, let's see if that one, that kind of looks like it's going to be rotation as well. And we see that as we rotate this around, there's 90 degrees going past it to, again, 180 degrees. Two of them are there. I think what we're looking at is the exact same description, except we're going to translate triangle 1 from, let's go ahead and A to B, and then rotate 180 degrees around, oh my goodness, around center B. Okay, so we know that for a fact the way that this was built was those pieces, but we also know a few other facts. It says find two pairs of line segments in the diagram that are the same length. Explain how you know they're the same length. Well, two pairs. I know that segment AB is equal to segment DC. How do I know that? Well, under rigid transformation, when I rotated this figure, translated and then rotated it under this sequence, I saw that AB maps AB. I also saw that over here, AB mapped CD. In either direction that we went, they were exactly the same. I also saw that segment EB is equal to segment AC. But I also learned that segment EA is equal to segment AD, which is also equal to segment BC. I know all of this because rigid transformation preserves, remember that word preserves means to keep the same, preserves length of segment, or we could just say segment length. So let's find two pairs of angles in the diagram that have the same measure. Well, here we go. Let's go with this. Angle EAB is equal to, this is a longer angle right here, must also be equal to this angle here in this triangle, angle DAC, which must also be equal to angle ACB. We have to see that all three of those angles must be equal to each other because, oh my gosh, I don't know why it does that, I'm sorry. Because these two angles are direct images of this angle under that translation and that rotation. So what we could really see is that each of these three angles in here, this next angle, angle ADC, is that smaller angle there, which is equal to angle ABC, which is also equal to angle EAB. So angle E, oh no, I messed up on the first one. This one should say angle AEB as the vertex. And this one, the vertex always goes in the middle here. This one should say angle EAB is equal to angle, where I put all these double congruence marks, angle ABC, which is also equal to angle, the double congruence marks, CDA. And we could say the same thing about this top one in the triangle as well. And why is that? Well, it's for the same reason. Rigid transformation preserves angle measures. This is the big idea right here with this entire lesson and with all of the other lessons that we've had to date, is that rigid transformation keeps the same measurements. It keeps the image exactly the same as the original. We can see that right here on this piece of patty paper, that this is my original and I made a copy of that, and then no matter how I manipulate it, whether I rotate or I translate or I reflect, that figure is still maintaining the exact same things. This angle is still equal to this angle, to the original angle. This angle is still equal to its original, and this angle is still equal to its original. This segment is still equal. You get the point, I hope, is that we don't change any elements of the measurements at all. We just change the position and the orientation of the figure as we move it about the plane. And we call that a preservation of the different components to keep it in that size. So here's an isosceles triangle. I think it's kind of funny that they call it 1. On side ON and OE have equal lengths. Angle O is 30 degrees. The length of ON is 5 units. Well, if we take a look at this and we understand a few principles about this, we can understand then that under rotation, if I were to rotate just this segment, ON, 30 degrees counterclockwise, it would match up with segment OE, which means that this segment must be of equal length. It would also mean that this degree right here is 30 degrees. It also tells us something about these two angles and their lengths, because we know that this is an isosceles triangle. So let's ask a few questions then. On the next page, it says reflect triangle ONE across segment ON and label the new vertex M. Let's see if I can do this with this paper. No, I have to get a new one. So I'm going to go ahead and reflect. I'm going to zoom out just a little bit here since this is so big. Go ahead and draw our sides. E, N, O, 30 degrees. And we're going to go ahead, it said, to reflect the triangle across ON. So we go across ON. It says label the new vertex. So the new vertex is the new vertex out here, the new point that I'm creating. That vertex is going to be a little trick you can use with patty paper right there to put transfer the lead, or transfer that lead over to there. Then we're going to go ahead and draw that triangle. And we're going to label that one, as it said, vertex M. And And now a couple things that we need to know about this. I'm probably going to be jumping ahead just a little bit. Actually, I won't jump ahead because that's not really fair to you. So we've drawn that, labeled it. What is the measure of angle MON? So we talked about back to here, angle MON. As we saw under the reflection, the picture that I had drawn on here and I reflected it, I see that it's still 30 degrees. That hasn't changed. It says, what is the measure of angle MOE? Well, under the measure of angle MOE, if I know that the original is 30 and the copy was 30 degrees, then I know together that they are 30 degrees and 30 degrees for a total of 60 degrees. Next question says, reflect triangle MON on segment OM. Label the points that correspond as N and T. So here we go. We're going to go ahead and go back to this one. OM. We realize it's the same triangle, so I can use the same drawing. Reflect it again across OM. And then we're going to label the point that corresponds to N. So what was point N, this one here, will now become point T. So from here, actually I'm going to just draw that one spot because that's the one point that I need to be able to translate or transfer across using my handy dandy trick here, my magic. We get that transfer of the information. Here. And we labeled that one as T. And then the next set of questions says, how long is segment OT? So how long is this one right here? Well, if from the beginning, the segment right here, ON, is 5 units, and then I reflect that across ON, it's still 5 units, and then I reflect that across OM, I see that that 5 units maintains all the way across all of those reflections. And I'm going to take this a step further. If that one was 5 units, and we knew at the beginning that the original two were 5, then every single one of these are 5 units long. So how do I know? Well, this is 5 units, and I know because reflection preserves segment length. I could have said right here instead of reflection, I could have said rigid transformation preserves that. But it's the exact same thing as this. Reflection is a rigid transformation, so it means the same thing. What is the measure of angle TOE? Wow, well, angle TOE is here to here to here. I now have another 30-degree angle. So I'm looking at 30 degrees times 3, which equals 90 degrees. And I'm just going to throw in the question, how do you know? Well, just for the how do you know, we would look at this. Reflection preserves. You know where I'm going with this. Angle measures. We could also say that rigid transformation preserves angle measures. If you continue to reflect each new triangle this way to make a pattern, what will the pattern look like? Well, it's going to continue to go around and around and around and around and around. So we're going to continue to see this pattern of a whole bunch of triangles moving all the way around. But here's the big question. If this set of 3 triangles makes 90 degrees, how many total triangles would it take to make a full circle? Hopefully you've paused the video for a second and think about that. If there's a set of 3 triangles to make up 90 degrees, that means my next 90 degrees will be 3 more triangles, and my next 90 degrees will be 3 more triangles. Well, what I can logically say with this, and I'm just going to do this just because I want to help with the visual, this would come all the way through like this, like this, like this, right? Just looking at 180 degrees, we double it, which means that we would double it again. I'm just going to sketch this in for here's these ones and these ones. I see 3, 6, 9, 12 times 3, or 12 times 30. And I know 12 times 30 is 360 degrees, but I also know 12 of these figures. That means we're going to have a 12-sided figure. What will the pattern look like? It will look like 12 triangles of the same size, rotating around center O. We would end up with a 12-sided figure. See, with this rigid transformation and understanding the concepts of it, we can understand what patterns will look like because those patterns continue to repeat using the exact same image. In art and in the art world, we call this a tessellation. It's where the same figure continues to build on itself to create a larger pattern. So with that, we're at the end of the lesson. Let's go ahead and wrap this up. Earlier, we learned that if we apply a sequence of rigid motions to a figure, then corresponding sides have equal length and corresponding angles have equal measure. That is still the major concept of this unit so far, is that corresponding sides have equal length and corresponding angles have equal measure. This fact lets us figure out things without having to actually measure them. For example, we can reflect this triangle ABC across sides AC to form a new triangle. It would look like this, where we see that angle of 36 degrees on angle CAB is going to reflect to another 36 degrees. Because the points A and C are on the line of reflection, they don't move. So the image of the triangle of AB prime and C, we know that angle B prime and angle B, or excuse me, let me back up. Angle B prime AC measures 36 degrees because the image is of its original angle BAC. We also know that the segment length of AB prime right here has to have the same length as segment AB. And what they didn't write on here is we also have to know that segment B prime C has to be equal to the length of segment CB. We also know that these angles right here must be equal to each other. We also know that these angles here, right? You catch on to what I'm saying here because, well, you're awesome and this stuff makes sense to you now. And I'm so glad for that because you've put in the hard work to understand these pieces. When we construct figures using copies of a figure made with rigid transformation, we know that the measures of those images of the segments and the angles will be equal to the measures of the original segments and the angles. We know intuitively now that if I draw a copy of this triangle right here, that every element of it must be exactly the same, or else the triangles don't match with each other. I hope what you've gotten over the last 10 lessons now is that simply sliding an object from one place to another, or turning the object, or flipping the object has bigger consequences that you've been building up for a long time. I am so proud of the work that you're doing. I am so proud of the growth that you've made with this. The number one thing as we work on this is please continue to develop that academic vocabulary that's going to be able to describe these motions and these figures in a way that is mathematical and follows all the rules that we've set forth. If you're still struggling with those descriptions, please continue to look back to lesson 4 at the lesson summary. There are great examples of that. Remember, you're doing an awesome job. You're doing great things, and don't you dare give up. Have a great day.